Last time we ended on this example, we wanted to know the rank of this matrix. We know that the rank of a matrix is equal to the dimension of the row space. So we needed to find a basis for the row space. The row space is the span of the rows in A. And we know that if we put the matrix A in reduced row echelon form, the reduced row echelon form's row space is the same as A. So that's what we did. We put that matrix into reduced row echelon form, and we saw that these two rows, the span of these vectors, will give us the row space. And because these two rows are linearly independent, they form a basis for the row space. So the row space of A was equal to the row space of the reduced row echelon form. And here's the basis for the reduced row echelon form. So that's also a basis for the row space of A. There's two vectors in this basis, so the rank, which is equal to the dimension of the row space, is 2. I'd like to also point out that once you get your matrix into reduced row echelon form, which is right here, the number of pivots is equal to the rank of your matrix. Notice that we have two pivots, and these two pivots correspond to the rows that are in the basis for the row space. So two pivots, the dimension is 2. The dimension of the row space is 2. And that's equal to the number of pivots, which is equal to the rank. Okay, let's move on. Here's an interesting fact that's based on the fact that we can put a matrix into reduced row echelon form and find the row space of the original matrix. For Rn, if you have a set S, and this set is spanned by some vectors in Rn, so V1 through Vr, where R is less than or equal to n, and you want to find a basis. In fact, this could be bigger than n, doesn't matter. So we'll just say you have R vectors, and you want to find a basis for this space S. All you need to do, now remember these are vectors in Rn, so they're column matrices. You can put them as rows in a matrix. So if you want to find a basis for S, put V1, V2, and so on as rows in a matrix. That is, write a matrix A as V1 transpose, V2 transpose, and so on, all the way to VR transpose. And put this matrix in reduced row echelon form. If you do that, then remember that the span of our original vectors, V1 through VR, you want to find a linearly independent set from the span. If you can find a linearly independent set, then that would form a basis for this subspace S. When we put these vectors as rows, we're going to put it in reduced row echelon form, and so the row space would be the same as the row space of A. So the row space of the reduced row echelon form is the same as the row space of A, and that row space is the span of those vectors here, which is going to be equal to this subspace. And that being the case, you'll have your linearly independent vectors. So the vectors, instead of vectors, I'm going to say the rows in the reduced row echelon form of A will be linearly independent. and form a basis for the subspace S. Let's look at an example of this. So a real example. Here I have that S is equal to the span of these 4 vectors. Now notice all of these vectors belong to R3. This set S, the span of these vectors, is a subspace of R3. Now if we want to find a basis for S, we know that it's going to have 3 or less vectors because the dimension of the space that it belongs to is 3. So which ones can we get rid of to form a basis? Now we could try to figure out which vector or vectors are linear combinations of the other ones. So like for example, if you saw that this one was a linear combination of these, you could get rid of that. Then you have to check and see if the rest of them are linear combinations. So maybe you try this one to write it in terms of these two, but then you see that you can't do it. And so maybe you need to try to write this one as a linear combination of the others. So you might have to do a lot of work. But instead, what you can do is you can just take the transpose of all of these, and you'll get a matrix that looks like this. So 1, 1, 0, 2, 1, 0, 1, 3, 1, and 0, 5, 5. So I just took the transpose of each one and just formed rows with that, made a matrix A. And now let's put it in reduced row echelon form. So to put it in reduced row echelon form, I'm going to keep the first row, so 1, 1, 0. I'm going to subtract 2 row 1 from row 2, and I'm also going to subtract row 1 from row 3. So let's do that. So this is 0, negative 1, 0. And this will be 0, 2, 1, 0, 5, 5. Now what? Well, let's see. We can add row 2 to row 1, and we could also multiply row 2 by 2 and add it to row 3. And while we're at that, let's multiply row 2 by 5 and add it to row 4. And we'll get 1, 0, 0, 0, negative 1, 0, 0, 0, 1, 0, 0, 5. And then let's multiply row 2 by negative, and let's also subtract 5 row 3 from row 4. And now let me ask you, what is the row space of this matrix, the reduced row echelon form of A? Well, the row space of A, which is also the row space of the reduced row echelon form, is a set of vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so then these vectors, if we take the transpose, S is going to be the span of these 3 vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. So actually S is equal to R3. You can get all of the vectors in S. All of those vectors are in R3, and all the vectors in R3 are in S. I didn't ask you to use these actual vectors to find a basis. I just asked you to find a basis. So by putting all these vectors as rows, we manipulated them and we found an easier basis to work with, which happens to be the standard basis for R3. Now we could get something else, depending on what the vectors are. This is just a nice way to find a basis. And look, you can see that all of these vectors are linear combinations of these. Let's move on. So we said that if we had the row space of A and we put A into the reduced row echelon form, then the row space of the reduced row echelon form is equal to the row space of A. And that's very helpful when we want to find the row space of A, because if we already know the reduced row echelon form, the row space is easy to find. But what about the column space? So what happens to the column space of A when you perform row operations to A? So remember, row operations are the same as multiplying A by elementary matrices on the left. So when I put a matrix A into reduced row echelon form, remember A is a bunch of columns, and if A is n by n, then we have n columns. And if we multiply on the left by some elementary matrices, then what's going to happen, so let's say we multiply EK, E2, E1, A, that's going to be the same thing as multiplying each one of these columns by these matrices. But when we multiply by a matrix, we're actually changing this column space. So this is a little sad, because if we're changing the column space, if we find the column space of the reduced row echelon form of A, that's not going to be equal to the column space of the original matrix A. However, when we're multiplying by these elementary matrices, all of these elementary matrices are invertible. So what's going to happen is the relationships between the columns is not going to change. So if you had that A1 is equal to A2 plus 4A3, well, you're going to have that same relationship with the reduced row echelon form of your matrix. So that's going to help you find the column space of A. So linear independence and linear dependence is preserved. Let's look at an example. So here I have the matrix A, it's 3 by 3, and we've seen it already. 1, 2, 4, -1, 3, 1, and 2, -1, 3. And I want to know what the row space and the column space of A are. Now we've already done the row space, so we can write this down again. So we said A, which is 1, 2, 4, -1, 3, 1, 2, -1, 3. If we put it in reduced row echelon form, which we've done, we saw that this was equal to 1, 0, 2, 0, 1, 1, 0, 0, 0. And we said that the row space was equal to the span of 1, 0, 2, 0, 1, 1. And that's because it's the row space of the reduced row echelon form. Now the column space of A is not equal to the column space of the reduced row echelon form of A. Okay? The column space of the reduced row echelon form, well, that's equal to you can see we have these vectors here. Column space is the span of the columns, 1, 0, 0, 0, 1, 0, 2, 1, 0. So let's put that here. 1, 0, 0, 0, 1, 0, 2, 1, 0. But look, these are the standard basis vectors for R3, and this one is a linear combination of these two. This is just 2 times this one plus 1 times this one. So we can get rid of this one. So the column space of the reduced row echelon form is just, and sorry, I should put a span here. So make sure you put span there, because it's not just these 3 vectors. It's the span of these 3 vectors. This is equal to the span of just these 2 vectors, because I can get the third one from the 2. That being the case, let's look at this. How we're going to figure out the column space of the original matrix is we're going to note the column space of the reduced row echelon form. The column space of the reduced row echelon form is the span of these 2 columns, and these form a basis for the column space, the reduced row echelon form. So then in the original matrix, these 2 are going to form the basis for the column space of A. So let's write that down. So the column space of A is going to be the span of the first 2 columns, 1, negative 1, 2, and 2, 3, negative 1. And in fact, like I said, the relationships between the columns remain the same. Remember how this third column here, we said it was 2 times this one plus 1 times this one? Well, this third column is going to be 2 times this one plus 1 times this one. Let's check. So if I take 1, negative 1, 2, and 2, 3, negative 1, and I want to get the third column, which is 4, 1, 3. So I said that this 2, 1, 0, which was this third column here, is 2 times the first plus 1 times this one. Let's see if I multiply this one by 2 and multiply this one by 1, add them, I get the third column. So we get 2 plus 2 is 4. The first one's correct. Oops. Correct. And then we get negative 2 plus 3, that's 1. And then 4 minus 1 is 3. So that's true. So the relationships between the columns of the reduced row echelon form are the same as the relationships between the columns of the original, but they're not the same column space. Notice that for these, the column space of the reduced row echelon form, I have a 0 in the third position. Here I do not have a 0, so it's obvious that the column spaces are not the same. Also, I want to mention that the dimension of the column space here is equal to 2, which is also equal to the rank, which is the dimension of the row space. In fact, the dimension of the column space will always be equal to the dimension of the row space. So another way to define the rank is you can say the rank is equal to the dimension of the column space. And the rank you can say is just the number of pivots in the reduced row echelon form of the matrix. Let's move on. Okay, I'm going to give you another problem. I want you to find a basis for the row space and find a basis for the column space of this matrix. I want you to find the rank of the matrix as well. So here's the matrix. It's a 3 by 4 matrix. See if you can find all of this information and then see if you get the same thing as I get. So go ahead, pause the video, and try to find the row space, the column space, and the rank. All right, so let's see if we get the same thing. So I'm going to put A in reduced row echelon form. I'm going to skip the steps on how to put it in reduced row echelon form. You should be able to do this. So I'm going to just write it out. I have 1, 0, 0, negative 10 sevenths, 0, 1, 0, negative 2 sevenths, and 0, 0, 0. Oh, actually, this is a 1. 1, 0. Okay? The row space is going to be the span of these three vectors, these three rows here. 1, 0, 0, negative 10 sevenths. That's the first one. 0, 1, 0, negative 2 sevenths. And 0, 0, 1, 0. That is the row space. These three vectors span the row space and they're linearly independent, which tells me a basis for the row space is just those three vectors. Now remember, don't put span of the three vectors. It's just the three vectors. Okay. Also, I want to point out, do not take the transpose of these matrices and put them as the row space because they're not rows. You don't want to write columns. Don't make that mistake. So here is the basis for the row space. And now we can answer the question of the rank of this matrix. The rank is equal to 3. Let's figure out what the column space is. Let's look at the reduced row echelon form of A. So this is the reduced row echelon form. And let's try to find all of the linearly independent columns. So here's 1, here's 1, and here's 1. And this last column is negative 10 sevenths times the first one, plus negative 2 over sevenths times the second one. So this one depends on the other three, which tells you in the original matrix, this one depends on these three. So the column space, let's copy this. Sorry, it jumped down. Scroll back down real quick. I think we're here. The column space, here we are. Is the span of these three vectors here. And these three vectors are linearly independent. So a basis for the column space is just negative 3, 1, negative 3, 1, 2, 8, 3, negative 1, 4. And if you want to verify that negative 10 over 7 times the first one plus negative 2 over 7 times the second one involving these. So this one, this column, is negative 10 over 7 times this one plus negative 2 over 7 times this one. You can check and see, and you should get this column. So we have a basis for the column space, a basis for the row space, and we have the rank of the matrix, which is 3, which is equal to the number of vectors in the basis of the row space, or the number of basis vectors in the column space, or you could just say the number of pivots in the reduced row echelon form of the matrix. Let's move on. Let's write down the definition of the null space of a matrix. So A, if it's an M by N matrix, we know that the null space is the set of solutions X that belong to Rn, such that A times X is the 0 column vector that's M by 1. So for example, if we have this matrix A, to find the null space of A, remember what we do. We make an augmented matrix, 1, 0, 0, 0, 1, 0, negative 1, 2, 0, put a row of zeros here, and put it in reduced row echelon form. Now the matrix I gave you is already in reduced row echelon form, so we solve for the pivots, this one, and we see that x1 is equal to x3, and x2 is equal to negative 2x3, and x3 is a free variable. So the null space is a set of vectors that look like r, negative 2r, r, where r is a real number. And a basis for the null space is just the vector 1, negative 2, 1. Because any vector here can be written as r times 1, negative 2, 1. So the span of this vector here. So the null space is the span of 1, negative 2, 1. That's a linearly independent vector, so that is the basis for it. Now, this isn't new, but what is new is what we're going to call the dimension of the null space. So the dimension of the null space, this is called the nullity of A. We just define it as the nullity of A, and for this particular example, the dimension of the null space, or the nullity of A, is equal to 1. That's the number of basis vectors in your basis, okay? And there's just one here. I want to bring your attention to something. How big is this matrix? This matrix is a 3 by 3 matrix. Notice that its rank is 2, because remember the rank is the number of pivots in the reduced row echelon form, and there's only 2 pivots here, right? So we have the rank is 2, and we said that the nullity is 1, and 2 plus 1 is equal to 3. What's this number right here? It's 3. That's interesting. Let's look at another example. Here I have a matrix B. This matrix, if you look closely, I saved you the trouble. This is in reduced row echelon form. See all its pivots, 1, 2, 3. Right now you can tell me what the rank of this matrix is. It's 3. Also, this matrix is a 3 by 6 matrix. 1, 2, 3, 4, 5. Oh, sorry, 5. 3 by 5 matrix. I can't count today. 1, 2, 3, 4, 5. Okay? Let's find the null space of this matrix. Well, I'm going to put this in an augmented matrix. Row of zeros here. Okay, it's already in reduced row echelon form, so I just look at this and I can see that if I solve for the pivots, I get that x1 is equal to negative 7x3 minus 2x5. x2 is negative 6x3 minus x5. And then x4 is equal to negative 7x5. Let's find the basis for the null space. How can we write these vectors? Let's put this in green. So we have, if we let x3 be R and x5 be S, let's rewrite this. The null space consists of vectors that look like -7R minus 2S, -6R minus S, x3, which is R, x4 is -7S, and x5 is S. So the null space is all such vectors where R and S belong to the real numbers. What is a spanning set? Well, notice that this right here is the same thing as R times -7, -6, 1. Let me make this a little bit bigger. So -7, -6, 1, -7, 0. This is an S here. It's kind of ugly, but let's make it look better. Plus S times -2, -1, 0. Oops, this is an S. So this should be a 0 here. -7, 1. Okay. All right, so we have found the null space is the span of these two vectors. So let's write that. The null space is the span of -7, -6, 1, 0, 0, -2, -1, 0, -7, 1. The dimension of the null space, or the nullity of B, is 2. Let's write that at the top, right beside the rank. The nullity is 2. 3 plus 2 is 5. What's this number here? It's a 5. That's very interesting. That brings us to a theorem. Just double checking to make sure I didn't mess anything up here. I don't think I did. This is called the rank nullity theorem. If we have a matrix A that's M by N, then N is equal to the rank of A plus the nullity of A. So if you know the size of the matrix and you know the rank of the matrix, you can find the nullity just by taking this in and subtracting the rank. That'll give you the nullity. That's how you can use this theorem. Or if you know the nullity and you want to just figure out the rank, N minus the nullity will give you the rank. Okay, the last problem we're going to do for this section is I'm going to give you a 4 by 5 matrix. So copy this down. We have a matrix. I'm not telling you what the matrix is, but I'm telling you the reduced row echelon form of it. Okay? What I am telling you is that it is a 4 by 5 matrix, and you can write this matrix A as a bunch of columns, A1 through A5. I'll also tell you 3 out of 5 columns. I'll let you know what A1 is, A2 is, and A5 is, but I'm not telling you what A3 and A4 are. What I want to know is, what is the matrix A, first off? Can you figure it out? After you find A, what's its rank? Then I want you to find the nullity of A using the rank nullity theorem. I want you to find a basis for the null space, and then I want you to verify that the nullity of A is correct. It's the same number that you found in 3. And that's it. So you can pause the video and try to figure this one out, or you can just watch what I do. Maybe at times pause it to try to think of what should be my next step and see if you get that correct. Alright, so I don't know all of A. What I do know is I know pieces of it. I know this column, and this column. What are these two columns? If I can figure that out, I know the rest of the matrix. Well, let's remember the definition of the column space. The column space is the span of the columns. And we know that the reduced row echelon form does not have exactly the same column space, but the relationships between the columns remains the same. Okay? So we don't know A3 and A4. So let's look at A3 or the reduced row echelon form of this matrix, its third column and its fourth column. This third column is 2 times the first one plus 1 times the second one. That relationship is going to hold in your original matrix. So A3 is 2 times A1 plus A2, just like this one. And then we can also say that A4, this fourth column, is 1 times this one, so is A1 plus 4 times A2. So that's what we're going to put in A. So let's make some space. The matrix A is -3, 5, 2, 1. That's the first column. 4, -3, 7, -1. That's the second one. We have a third column and a fourth column, and then the fifth column is 1, 2, 9, 1. Let's follow this rule here. A3 is 2 times this one plus 1 times this one. So you might have to, I'm going to actually write it above. So 2 times -3 plus 4, that's -6 plus 4, which is 2. So I'll put a 2 here. Okay, the next one is 2 times 5 plus -3, that's 7. Then 2 times 2 plus 7, so that's 4, 11. And then the last one is 2 times 1 minus 1, which is 1. So just double check. I think this should be -2, right? 2 times this one, that's -6 plus 4 is -2. Then 7, 11, okay, I think I'm happy with that one. Then we're going to do A1, -3 plus 4 times 4, 16, 15, 14, 13, okay. Then 5 plus 4 times -3, that's -12, that's -7, okay. And then the next one is 2 plus 4 times 7, that is 28, 30, and then the last one, 1 minus 4, that's -3. Just double check, -3, 13, 7, 30, okay, and then, okay, I think I'm happy with that. So this is A. Now let's find the rank of A. For the remaining questions, we actually don't even need to use this matrix A because all of them can be found from the reduced row echelon form. So the rank of the matrix is the number of pivots. 1, 2, 3. The rank is 3. The nullity of A, we're going to figure it out by using the rank nullity theorem. What size is this matrix A? This is a 4 by 1, 2, 3, 4, 5. N is 5. So the rank nullity theorem says that the rank of A plus the nullity of A is equal to N. Here we know that N is 5. So 5 is equal to the nullity plus 3 because that's the rank. So the nullity is 2. Let me write this. The nullity of A is 2. Okay? Number 4. Let's find a basis for the null space of A and verify that the nullity is correct. For the null space, we just need to take the reduced row echelon form of the matrix, which is right here. Copy it. Put it down here. I'm going to erase this and put a column of zeros and see what we get. We see that x1 is equal to negative 2x3 minus x4. x2, we're solving for the pivots, is negative x3 minus 4x4. And then x5 is 0. So let's just double check. Sometimes when I talk, I don't write down the right thing. I think that's right. So the null space consists of vectors that look like negative 2r minus s, negative r minus 4s. It's x1, x2. x3 we're letting be r. x4 I'm going to let be s. Also be careful here. Make sure you put them in the right order. Sometimes that, especially if this is like, we know we solve for x1 and x3, but x2 is free. We put them in the wrong order. You'll get the answer incorrect. And then x5 is 0. This is equal to r times negative 2, negative 1, 1, 0, 0, plus s times negative 1, negative 4, 0, 1, 0. And here we have our basis. So the null space is the span of these two vectors. And that being the case, you can see that we have two basis vectors. So the basis is just these vectors. I want to remind you, don't put span of these two vectors. That would be the whole space. I just want the basis, and it's just these two vectors. And you can see that the nullity of of the matrix A is equal to 2, just like what we had expected to find, the nullity being 2. Something else I could ask you, what is the column space and the row space of A? Well, the column space is going to be, remember that we look at the column space of the reduced row echelon form. These three, not that one, sorry. These three are linearly independent. You can see that. You can see that these two are combinations of these two vectors here. So A1, A2, and A5 will be a basis for the column space. So A1, A2, and A5, that is, if you take the span of these three vectors will be a basis of the column space. The row space is the row space of the reduced row echelon form, which is this one, this one, this one, and this one. And keep them as rows. And that's it.